Hello everyone, so today I'll be starting on my first video of my second video series, which will be on materials characterization for semiconductor devices. So let me first go through an outline of this series. So this series is a follow-up series to my previous series, which is on materials engineering for semiconductor devices. So while my first series largely focused on the process engineering aspects on how to synthesize and fabricate a semiconductor device, this series focuses more on the materials characterization techniques used to basically analyze the semiconductor devices produced in the fabrication steps outlined in the first series, as well as to determine whether the fabrication process is going well or not. So for this particular series, the outline will be roughly as follows. So in this first video, I'll go through a bit of the principles on device failure, as well as some electrical characterization. In the second video, I'll undergo certain optical metrology techniques like scatterometry and ellipsometry. In the third video, I'll cover electron microscopy and related techniques. More specifically, I'll first cover SEM, scanning electron microscopy, and in the fourth video, I will cover transmission electron microscopy, TEM. And in the fifth video, I'll cover AFM, atomic force microscopy. In the sixth video, I will cover secondary ion mass spectroscopy. Subsequently, I'll talk about X-ray photoelectron spectroscopy, and I'll conclude this entire series with a pretty interesting topic of vibrational spectroscopy encompassing Raman FTIR as well as AFM-IR, which is a very interesting and useful technique. So let's begin on the first chapter, which is on device failure and electrical characterization. So let me first say a certain disclaimer. My background, which is my bachelor's degree, is in material science and engineering. So actually not in electrical engineering. So actually this aspect of electrical characterization is not my particular area of specialization. I'm more specialized in the area of characterization of the material properties and material structure. However, nonetheless, I will give an introduction on this particular chapter because I think it's very important for overall holistic understanding of this particular program. However, if you want to learn more, I'm sure there are many other resources out there that go into greater depth and technical rigor than what I'm able to go through today. So let me first recap the MOSFET operation. So shown over here is N-channel MOSFET. So as mentioned in our previous series, how a MOSFET operates is that it's basically the channel current is controlled by the gate. When a certain gate voltage is applied, in this case, when a positive gate voltage is applied, it eventually attracts electrons to form an inversion region, which will be your N channel that will connect the source and the drain, allowing in this case charge carriers, in this case electrons, to flow from the source to the drain. Therefore your transistor will be in the on state. So the most important characteristic of a MOSFET transistor is the existence of the threshold voltage. So at gate voltages below the threshold voltage, it is insufficient to create the inversion layer in the channel region, and therefore there is no source to drain current because there's no channel that allows for the charge carrier conduction to occur between the source and the drain. And when gate voltage is higher than the threshold voltage, we see that the channel is formed and basically current is able to flow from the source to the drain. And the larger the gate voltage, basically the wider, or you can say the deeper, the channel region will be formed, and therefore increasing the kind of current carrying capability of the channel region. Therefore the current, source to drain current, will increase as gate voltage increases. Now let us take a look at the graph of the source to drain current plotted against a source drain voltage as the x-axis at two gate voltages, of course one smaller and one larger. And of course expectedly, if gate voltage is basically larger than the threshold voltage, alright, source to drain current is able to flow with the larger gate voltage, allowing a larger eventual current to be achieved between the source and the drain. So one thing we notice is that when source drain voltage increases past a certain point, they reaches a saturation region, and that's because the pinch off effect starts to be observed, where even though your drain current your drain voltage, your source drain voltage is increased continually, current does not continue to increase because the pinch off effect means that there's a limitation and eventual plateau of the current that's able to flow from the source to the drain. So this was covered in greater detail in the first video series, and you can refer to that for a more in-depth explanation with a greater number of diagrams. And so, however, because this particular chapter is talking about the electrical characterization of the MOSFET transistor, so we need to go into a slightly more technical discussion of the IV curve that we've shown before. So this is the IV curve of the drain current against the gate voltage. And so as mentioned before, there's this idea of the threshold voltage. And when the transistor is in the on state, we can define what is known as the transconductance. Transconductance is basically the first derivative of this graph of your D current over the gate voltage. So the important question to ask is that how is the threshold voltage defined? Because even though it seems like a sudden change over here, but of course it is a continuous kind of graph. So we still need to define a certain cutoff point or a certain algorithm by which we can basically define the threshold voltage with a consistent definition that can be applied for all cases. So of course, the most straightforward case is to just set a certain threshold level, say that when the drain current exceeds 0.1 millivolts, for example, or whatever, then that will be defined as your threshold voltage, the voltage where the drain current exceeds this predefined, user-defined threshold level. However, of course, that may be slightly problematic, right? So another more commonly used way is to plot the first derivative graph. So if you plot the first derivative graph, remember the first derivative is also known as the transconductance. We get a graph that seems something like this, and we see a region where we can call the linear region, where your basically plot of transconductance against gate voltage appears almost linear in shape, and we can draw a straight line, right, to fit this linear region, and the intersection between this straight line and your horizontal axis can be defined as your threshold voltage. So this is a very common definition of threshold voltage that is used, and of course in modern data collection system, curve tracing system, of course all this can be these definitions can be, I guess, programmed into the data collection system. And another very important parameter that is obtained from the IV curve is this idea of subthreshold swing. So to actually calculate subthreshold swing, we plot the drain current in a logarithmic scale. Right here, over here in red, you see it's a logarithmic scale. So the difference between, let's say, 10 to the power minus 5 and 10 to the power minus 4 is often called 1 decade of current, because it's 1 unit in log base 10. So it's called 1 decade of current. So 1 over the slope of this graph in logarithmic scale in the region before the threshold voltage, known as the subthreshold region. So 1 over the slope is known as the subthreshold swing. And so what we want is that we want the subthreshold swing to be as small as possible, so that your slope over here will be as sharp as possible. So what is this? So what's the physical meaning of this? Okay, so if we have a steeper slope and therefore a smaller subthreshold swing, for a certain voltage below the threshold voltage, the leakage current from source to drain will be smaller. Because remember, below the threshold voltage, in the subthreshold region, ideally we would have zero source to drain current. Right, we will have zero source to drain current. So any non-zero value of source to drain current can be called a subthreshold leakage current. So if we have a steeper slope and a smaller subthreshold swing, we will be able to have a smaller subthreshold leakage current from the source to the drain. And that's good, because we do not want a leaky transistor when the transistor is supposed to be in the off state. And another way we can think about it is that if the slope is steeper, for every increase in gate voltage in the subthreshold region, there's a larger increase in current. So this means that there's a greater control of your gate over your source to drain current, and that's of course desirable, because in a transistor what you want is you want the gate to be the means of control over the source to drain current. However, of course, we can prove through certain device physics that for a MOSFET transistor, there is a hard limit as to how low subthreshold swing can go, and that it is physically not possible to go below this value in a MOSFET architecture. However, I will not go into that amount of detail because my background is not in this kind of device physics and electrical engineering. So, however, as mentioned earlier, right, the MOSFET is not a real MOSFET transistor is not the same as an idealized model, and in reality, we have various forms of leakage current. So, one kind of leakage current is, as mentioned earlier, the subthreshold leakage current. So that is when below the threshold voltage, there's still current flow from the source to the drain. So that is shown in the red arrow over here. We also have, of course, tunneling current through the gate oxide. Remember, the gate oxide is an insulator. It should not conduct any current. However, it's possible for there to be some current flow, as well as it's also possible for there to be other leakage currents, such as leakage current to the junction, right, to the base, the box silicon. And so on and so forth. And so what are certain factors that can exacerbate this kind of leakage currents? Of course, one of them is the short channel effect. So a bit of background here is that the trend, of course, for improved transistor performance is the smaller and smaller transistors, right? That's the sort of, decrease from 7 nanometers to 5 nanometers to 3 nanometers to 2 nanometers, they are saying in all the leading edge foundries in the world today. And the reason for this is because a smaller transistor allows for better control of the gate as well as a greater power efficiency. However, there also exist certain drawbacks, and one of them being the generic category of short channel effects, which is basically certain non-idealized behavior of the transistor that tends to occur when the channel becomes shorter and shorter. So one of the effects is the Hot carrier effect. So when the channel becomes shorter and shorter, at the area where the channel pinches off to the drain, right, there builds up a large electric field, right? There's a large electric field build up, and at this, when there's a large electric field building up, there will be a large electric force being being applied onto your charge carriers, and your charge carriers will then be accelerated to very high velocities. And when your charge carriers are accelerated to such high velocities, they can easily enter into regions that they're not supposed to enter to. For example, they can have sufficient velocity to travel to the substrate, to the base, therefore forming the leakage current shown below over here in this dark red arrow. In addition, right, it can also go the other way. It can go into the gate oxide, and so when the charge carriers are traveling at such high velocities into your gate oxide, it's easy for them to break certain silicon and oxide bonds, for example, in your gate oxide, therefore creating things like interface traps, creating trap charges in the oxide, or that, which will of course degrade the transistor performance, because in an idealized transistor there should be a pretty good interface with as few interface trap states as possible and as few trap charges in the oxide block material as possible. However, so these hot carriers can actually cause this kind of damage to the oxide as well as the interface. So the second one is slightly more difficult to understand, is drain-induced barrier lowering. So the idea is that when the channel is short enough, the voltage being applied at the drain is able to influence the kind of barrier that exists in the channel when the transistor is in the off state. So when the transistor is in the off state, basically due to the band diagram of the semiconductors, which I forgot to show here, but I guess we probably don't have to go into that depth. But due to the, you can draw the band structure and can show at when the Fermi levels align at equilibrium, right? In the absence of a gate voltage, there will be an energy barrier throughout the whole channel that prevents basically source to drain current flow when the transistor is off. However, when the channel is short enough, right, the influence of the drain voltage, right, the drain voltage pushes the energy level of the drain side down, and so that can also kind of push the energy level in the channel down a bit, and therefore this is original energy barrier, right? The original energy barrier is now lowered. So you can think of this as like the mountain that the ball needs to roll over. So without this barrier, right, the ball can roll from source to the drain. It goes down here, right? But there's this hill right now over here, right? So it prevents the ball, which is my laser pointer cursor, from going from the source to the drain. It has to go up the hill, right, which is energetically unfavorable. However, with the DIBL, we see that the hill becomes smaller in size, right? Smaller in size, lower in height. Therefore, it is possible for there to be a larger subthreshold current flow right now to occur even when the transistor is in the off state, right? Because in the subthreshold region, the transistor is in the off state. So what is the effect on the IV curve? So this is the IV curve of the source to drain current plotted against the gate voltage, right, plotted in the logarithmic scale. That's why in the subthreshold region it is a linear kind of relationship, because your drain current is plotted in this particular plot in the logarithmic scale. And so what we actually observe is that when there's a drain induced barrier lowering for the same gate voltage below the threshold voltage, there's now a larger drain current, right? So a much larger drain current, in fact. And so that represents a much larger subthreshold leakage current, and it represents a leaky transistor even in the off state. So that is not desirable. Okay, so in addition to failures as well as non-idealities that can occur in the transistor, so at the device level, in the back end of line, so all your interconnects, right, there can also be failures that occur, and that which is very important to catch these failures in semiconductor fabrication. So I would like to first do a recap on how these interconnects are usually fabricated in the modern era of a copper interconnects, right? So nowadays, most of the more advanced nodes all rely on copper interconnects. Due to reasons I mentioned in the previous video series already, but it has got to do with electron migration and all that. But because of the certain peculiarities of the copper fabrication process, which I also mentioned in the previous video series already, it has to be fabricated using a Damascene process. So the Damascene process involves first the deposition via chemical vapor deposition of your low-K dielectrics. Why a low-K dielectric? I mentioned again, I won't mention again. So subsequent to the deposition of your low-K dielectrics, there's a lithography to define the patterns, and subsequently the plasma etch of your dielectric to form your vias and trenches where your copper metal needs to go in. Where copper metal cannot be directly filled in, right? First, a barrier layer, usually of titanium nitride or tantalum nitride, is deposited, followed by a seed layer of copper to make it conductive for the electroplating of copper. And so this is normally done using a PVD, physical vapor deposition. Then after that, you can do electrochemical plating of the copper in an electrochemical bath. And after that, the surface will of course not be even. We need to use a CMP to polish the surface down to make sure it's flat and all that. So the kind of failures that can occur in the back end of line is the formation of voids in the interconnect. So over here, we see the formation of the void is not that severe, but if the formation of the void is large enough, it can cause the case of even a complete short in the circuit, right? So in this case, it's probably just result in an increased resistance, but for the case where the void is larger, it can even cause a complete, sorry, not short, open in the circuit, a complete open in the circuit. So, however, in addition, right, to void formation, we can also see the formation of certain halox, right? Because after all, right, if material leaves a certain area, right, forming a void, it needs to appear somewhere else, and where it appears, it will form a halox, right, which is a protrusion of your metal material, and that is the one that can cause short circuits, as well as other undesirable effects. So what are the causes of this void formation? One of the major causes of void formation is this idea of electromigration and stress migration. So for electromigration, which I think I also covered in one of the videos of my previous series, the idea is that there's this electron wind when current flows. So for example, when current flows, the conventional current flows from left to right, right? Electrons actually flow from right to left. And this electron actually bombards, right, the metal atoms that exist in the interconnects, and it exerts a certain force, right, through these physical collisions that causes the metal atoms to drift, right, in the opposite direction of conventional current flow over a period of time. So forming voids on one end and halox on the other end. Now, how about stress migration? Stress migration involves the migration of the metal atoms from areas of compressive stress to areas of tensile stress. And vacancies, right? You can think of it also as vacancies moving from the area of tensile stress to the area of compressive stress, right? I hope this makes sense to you, right? Why the direction is such, right? Because in areas of compressive stress, right, there's not enough space, right? So vacancies will move there, and atoms will move out of there, right? I hope that makes sense to you. So what is the reason for certain areas having compressive stress and tensile stress? That's because deposition is often conducted at higher temperatures. So when deposition is conducted, let's say at an elevated temperature of 800 degrees, for example, at that temperature, maybe there is very little stress in the material, right? The material is able to move, atoms are able to move in such a way that minimizes the stress, right, in the geometry of the interconnects. However, after that, when the wafer is cooled down to room temperature, right? Cooled down to room temperature, there's a temperature difference, right? And due to differences in coefficient of thermal expansion, right, of your metal, your dielectric, your silicon substrate, certain stresses can emerge in certain areas of your metal interconnects, and so that will result in stress migration. So a key contributing factor is what I mentioned, this difference in the coefficient of thermal expansion and therefore of contraction as well. You know, when you have this kind of increases in temperature and cooling down of your wafer. And so there can be this interplay between your electron migration and stress migration in the realistic situation that will cause the formation of voids in your interconnects. Okay. So now enough talking about interconnects. Now let's talk about the gate dielectrics, right? Or dielectrics in general, but I want to specifically focus on the gate dielectric, also known as the gate oxide. So I'd like to bring once again to your remembrance, this CV, which stands for capacitance voltage graph of your MOS stack, so your metal oxide semiconductor stack. And so do I need to explain again why this curve comes about? Okay, maybe I'll explain again because I later want to talk about how certain defects in the oxide will alter this curve. So initially in the accumulation region, right, where the voltage in this case is the gate voltage is above the flat band voltage, right? Or you can think of it as in this case this is a P substrate. So okay, this is a bit wait, let me take a look at this. Okay. Yeah, so in this case, this diagram is actually a bit different. It should be opposite of this. So this is the case for P substrate, but I think this is the graph for the case of an N substrate. So, but never mind, just bear with me. I'll just do a quick explanation with the diagrams that we have here. So, but in the accumulation region, so for example, in this case, a P substrate, we are applying a negative gate voltage. So we are attracting the positive charge carriers, which is the holes from the P substrate, of which there's a large abundance of. So basically we only observe, right, one capacitive layer in this stack, and that is the gate oxide layer that is acting as the capacitor. However, in the case of when we are applying a positive gate voltage, so it repels the majority charge carriers in your P substrate. So it's repelling the holes away from the interface between your oxide and your semiconductor. And so what we observe is the formation of a depletion region. So in this depletion region, there is absence of charge carriers, right? Because your charge carriers, which is the holes in the p-type material, has been repelled away from this region. So we can think of this region to be also a non-conductive layer. And so now we can think of the capacitive region as having been expanded, right? Now not just your oxide layer originally, which is of course capacitive in nature, but also your non-conductive depletion layer as well. So that's the depletion region. And when the capacitance becomes larger in size, right? And the capacitive layer becomes larger in thickness, we observe a decrease in the capacitance, right? Because I'd like you to recall the equation for capacitance, right? Is basically capacitance has an inverse relationship with the thickness of the capacitive layer. And however, there reaches a point where there's this inversion that occurs. So in this case, the gate voltage is larger than the threshold voltage, and so it's large enough that now it's able to attract electrons out of the p-type substrate. So normally the p-type substrate contains holes, right? However, in this case, the voltage is large enough that's able to break certain of the chemical bonds in the silicon, in the p-type silicon, and therefore pulling up electrons from the p-type substrate. So these electrons will gather at the oxide and silicon interface and therefore form the inversion layer. So at the high frequency AC modulation, we can think of this as the depletion layer stops growing in thickness. However, the depletion layer is still seen by the AC modulation, and so therefore we see that the capacitance of the entire stack plateaus at a constant level. Right, plateaus at constant level. However, if the AC modulation that's applied to the metal oxide semiconductor stack is of a low frequency, the inversion layer itself can respond to this AC frequency, and therefore the measurement will not be able to see in that sense, you'll not be able to see the inversion layer, and therefore the only capacitance that is observed, right, is the oxide layer, and therefore the capacitance of the entire stack goes back to the original capacitance of only the oxide layer that we saw in the accumulation region. Okay, so hopefully that prompted your memory. Yeah, apologies for the a bit of the incoherence between the diagram and the graph, right? Because by right the graph should be flipped over, right? Where the negative region is your accumulation region and the positive region is your inversion region, but it's the other way around in this graph. So apologies for that. Hey, but you get the idea. So what is the consequence, right, when there are certain non-idealities in the oxide? So non-idealities can be, for example, certain fixed charges in your oxide, or certain traps in the interface between your oxide and your semiconductor. So if there are certain fixed oxide charges, it is a simple horizontal translation of your CV kind of curve. And the reason for that is because this fixed charges in the oxide layer will kind of screen out the voltage being applied at the gate, and therefore you can think of it as the silicon, the doped silicon layer below the oxide not being able to see the full extent of the gate voltage applied, because there's the fixed charges in the oxide that kind of screens out the voltage that's being applied at the gate. And so therefore we require a larger gate voltage to reach the threshold voltage, or you can think of it as a leftward shift or rightward, right, depending on whether it's a p-type or n-type substrate, but basically an increase in the absolute value, right, of your threshold voltage. So yeah, that is how fixed charges will affect the CV curve. As for the presence of certain interface trap states, right, there will be a distortion, a kind of spreading out of the curve, and that is because interface trap states can be occupied rather by charges, right, by your charge carriers, and therefore it will be a stretching out of your CV curve. Okay, and so therefore, right, measuring these CV characteristics is gives us quite important information as to what's the quality of your gate oxide, as well as the quality of your oxide and silicon interface, which is of course very important for your transistor characteristics. Okay, so now once again talking about gate oxides, right, what happens when your gate voltage is too large, or let's say a certain gate voltage is applied for too long a duration? What can happen is dielectric breakdown. So how is dielectric breakdown measured? It's measured by having the dielectric or a device basically sandwiched between two electrodes, right, and a constant voltage. Normally it's a constant gate voltage that's being applied to your gate dielectric. And so what happens is that initially, right, your gate current will be a very, very low value, right? However, there reaches a point where there starts to be soft breakdown. So SBD stands for soft breakdown. So certain current carrying pathways may start to be formed in your gate oxide, or certain basically your charge carriers can maybe utilize certain trap states, right, that starts to be formed in your gate oxide to form a current conducting path through your gate oxide, and therefore your gate current starts to increase. So there can be multiple stages of soft breakdown. However, there eventually reaches a certain point in time right? Where the voltage has been applied for sufficiently long period of time to trigger your hard breakdown. And so at your hard breakdown, you see a large spike in your gate current, and that is normally defined as your time to failure. The start time of the test to the time of hard breakdown is often defined as a time to failure of your dielectric. And so let me talk a bit about the kinetics of dielectric breakdown. So basically, dielectric breakdown can be actually described using various models. So of course, the first model is the Schottky emission model, where there's basically overcoming of your uh, barrier, right, of your barrier between your the Fermi level of your metal to the conduction band of your insulator. So of course, any emission by this mechanism will likely to be not very fast, right? Because there still needs to be an overcoming of the energy barrier from your metal's Fermi level to your conduction band level of your insulator layer. However, if your insulator, for example, is very thin, there can be direct tunneling, right, through the quantum effects. There can also be Faulkner-Needham tunneling. This occurs when the voltage applied across the insulator is very large, causing there to be a large uh, gradient of your conduction band of your insulator. And so we realize that to tunnel across right now, instead of tunneling across the whole width of the insulator, right, because the band has been brought down to such a large steep descent, right, the tunneling can occur more easily through a shorter space, right, a thinner layer, so to speak. So that is Faulkner-Needham tunneling. There can also be a Poole-Frankel emission, where basically the charge carrier, your electron, for example, hops like into a trap state, then it hops into the next trap state, then it hops into the next trap state. So all this hopping, right, there's no tunneling in that sense. So it's called Poole-Frankel emission. Right? There can also be trap-assisted tunneling, where it goes from trap state to trap state, but between trap state, instead of hopping, right, it just tunnels through. Right, through quantum tunneling effect. So how do we know, right, what mechanism dominates in a particular case? It's good because the physicists have already computed the kind of expected relationship of current against voltage that is expected to be observed for all these kinds of models of dielectric breakdown. For example, if the plot of ln of your current against your square root of voltage, gate voltage in this case, is linear, then most likely it follows a Schottky emission mechanism. However, if it's the plot of ln current over voltage against square root of voltage that gives you the linear relationship, then most likely it's a Poole-Frankel emission mechanism of your gate oxide current, leakage current that's occurring. Okay. So remember earlier I talked about the hard breakdown being defined as the point where the time to failure is measured, right? So it turns out that this time to failure of your dielectric follows a Weibull distribution, which is a certain statistical distribution. So remember, time to failure, if you have 100 devices, the time to failure of your 100 devices will not be exactly the same, right? Because this is the real world, right? It's probabilistic in nature, right? It's a random variable. So therefore, the time to failure in real life experiments tend to follow a Weibull distribution. And so the unique thing about this Weibull distribution is that there's a certain way that we can linearize it by plotting a certain transformation of the cumulative failure probability against lifetime, or transformation of lifetime. So this is basically a mathematical kind of procedure that will be taught in your reliability engineering classes. So if you're interested, you can be like me and take a reliability engineering class and learn a bit more about this. But anyways, the idea is that these plots are normally called the time-dependent dielectric breakdown plots, or TDDB. So it shows you how the time to failure changes when the constant voltage applied is different. So for example, if the constant voltage stress that's applied to your dielectric layer is 2 volts, right, versus 2.2 volts, right, there is a leftward shift in your time to failure. So there's your time to failure is now smaller when there's a higher stress being applied, which is of course, very, very reasonable and to be expected. When you have a larger stress, of course your time to failure will be smaller. Nothing strange about that. So I just would like to mention this graph. Okay, so now I'd like to mention about the test structures, because previously we talked about measuring the IV curve of the transistors and all that. But do we actually want to measure the transistor in the device, like, let's say, during the fabrication process, right? That's not entirely ideal for various reasons, right? Firstly, we may not want to disturb the actual chip, right? The actual transistors in the chip. Secondly, the actual transistors in the chip may not be accessible to our micro probes, right? Because maybe the interconnects haven't been connected well yet, properly finished yet, or maybe the interconnects are connected in a way that it's not possible to isolate a single transistor, right? That's very possible. So we have normally these kind of test structures that are fabricated in the scribe lines. So the scribe lines are the areas between the chips that will not form part of the chip. In fact, the wafer are normally diced along the strap lines to cut along the strap lines to form the individual chips. So this is considered unused space, so to speak, that's not used to make the actual functional chip. So often, right, we design test structures in this scribe line. So these test structures are simple structures of certain metals, maybe sometimes certain simple patterns that are being created. And so these patterns normally have a dimensions, right, comparable to your device dimensions in your chip. So the idea is that if your fabrication process fails to produce good test structures, most likely it also will not produce good transistors in your chip. So if testing these test structures shows that these test structures are not created as designed, most likely your transistor in the chip or also not created as designed, there'll be problems, right? So this test structure is used as a proxy to measure the basically the how successful the fabrication process has been. So these test structures can be simple lines, crosses, and whatever. And with probe pads that allow you to put your micro probes to measure your electrical properties of these test structures. So how do we do this probing, right? You may think, oh, we can just put two probes, right? One on the left, one on the right, and measure the resistance of the test lines, right? Through these two probes. However, what is the problem with this, right? The problem with this is that your probes themselves have resistance, right? There's a resistance of your probes, right? That's used to measure the resistance of your scribe line. Additionally, at the contact between your probe and your test structure, right, there is also a contact resistance, right? This contact resistance can be made particularly large if your pad or your probe has a certain oxide layer that could be formed over exposure to air over a period of time, right? So we have to understand that there are these contact resistances as well as the probe resistances that will basically be added on to your resistance of your device under test. And it's not possible in a two-point probe setup to distinguish the resistances of your contact and your probes from the desired resistance of your device under test, right? So we cannot accurately determine the resistance of your device under test. So what is the solution to this? The solution to this is the 4-point probe method. So in the 4-point probe method, two probes are used to pass your current through your device under test, right? And so that is your ammeter over here, or basically you measure your current flowing through these two probes. And basically the probes to measure the potential difference across your device under test are two separate probes. They are connected to an extremely high input impedance voltmeter, such that there is close to zero current flowing through the two probes that are used to measure potential difference. So we are isolating your current measurement from your potential difference measurement, such that in this case, effectively, we can remove the resistances of your contact resistance and your probe resistance from the measured resistance. Okay, so the resistance of the device under test can be simply calculated as the potential difference measured by the voltmeter divided by the current measured through the other two probes. And in this way, we can eliminate the probe resistance and contact resistance from the measurement of your resistance of device under test. So in the case of measuring the resistance of a thin film or certain surface of the semiconductor, we generally have the four probes, the four probes of your 4-point probe method are evenly spaced, and this allows us to actually use a very convenient expression to find the resistivity and therefore subsequently sheet resistance and of your semiconductor thin film or semiconductor surface. Okay. However, for the case of a test structure, your 4 points will just go to your 4 probe pads lah, right? Okay, however, right, of course, this, for example, these measurements of your resistivity and sheet resistance, sometimes you need to introduce correction factors, right, to correct for certain approximations that this expression makes in terms of geometry and all that. However, I'll not go through that in this program today. Right. So I'd like to kind of end off this video by talking a bit about inline and offline characterization. So inline inspection systems are inspection that are conducted, in the manufacturing line, right? Along the manufacturing line. So maybe in between your deposition and your CMP, or in between your etch and your deposition, right? There can be a certain inspection of your wafer. So these are called inline inspection. So one example is your optical inspection, which I'll cover in the next video, that for example can count the number of particle contamination on your wafer just after it finishes a step in one machine before going to the next machine. So this is inline, and it's very important because it allows for detection, be between the various steps of your manufacturing, your wafer fabrication. And so that's important because we want to detect any defects early so that we don't waste precious time and money. Okay. However, there's also this idea of offline characterization where your wafer, let's say a wafer has been found to have too many defects, or too many contamination, too many defects, and so that wafer is then taken out of the line, and then let's say the particle contamination that we've detected earlier is then analyzed with SEM, which we'll cover in future, and the particle elemental composition is analyzed using EDX, for example. So that is called the offline characterization, and it's very important step for us to determine the root cause of this defect, because ultimately we want to find out what causes all these defects, right? And so likewise, your electrical characterization, right, is most of the time is actually an offline characterization where your microprobes are assembled on your wafer and your electrical measurements are taken, usually on your test structures. Okay. So this marks the end of this video. Hopefully it's not too confusing. I decided to try to strike a balance between comprehensiveness and rigor, right? Because I want to be comprehensive, but I don't want to go into too much rigor because it will be maybe hard to absorb, and also I'm also not really the subject matter expert to go into exceptionally deep rigor for this particular video. However, in subsequent videos, maybe I can actually share more, right? Even because it'll be my area of particular specialization. However, in the next video, I'll talk about sclerometry and ellipsometry, which are optical methods of wafer inspection. And these are extremely important techniques. I hope you will enjoy the next video as well. So thank you for watching this video. I hope you enjoyed this video.